Hello everybody, my name is Kiran. I am working as an assistant professor in the department of EEE Anits. I welcome you all to my fourth lecture under the first module DC generators. In my first lecture, discussed the construction details of DC generator. In the second lecture, I discussed the working of DC generator and how a commutator is playing a crucial role in the working of DC generator. In the third lecture, I discussed or derived the EMF equation of a DC generator. In today's lecture, we are going to see the classification of DC generator. So my electrical machine can be classified generally into two categories, that is DC machine and AC machine. DC machine further can be classified into two categories. One is DC generator and DC motor. So now our focus is only on DC generator in this module. Okay, so similarly AC machines can also be further classified as asynchronous and synchronous machines as well as transformers. So again, a synchronous machine is classified as induction motor. Synchronous machines can be classified as synchronous motors and alternators. And again, induction motor, we have two types, single phase and three phase induction motor. So now AC machine is not our concern in this module. So in this module, we are only concerned about the classification of DC generator. Okay, so DC generator are classified into two categories. One is self-excited DC generator and separately excited DC generator. Self-excited DC generator are further classified into two categories. One is shunt generator, second is series generator, third is compound generator. Compound generator again is further classified into two categories: long shunt compound generator, short shunt compound generator. Again, individually are further classified into two categories. One is cumulative and another one is differential. So we'll see the governing equations and the circuit configuration of all these types of generator one by one in today's lecture. For separately excited DC generator, this is the circuit configuration of separately excited. So as you can see, the field is separately excited by a DC source. That is why the name separately excited DC generator. So I can define separately excited DC generator as a generator whose field winding or coils which are energized by a separate or external DC source. So the power delivered to the load in this case can be given by V into IA or V into IL, where IA is armature current. You can see from the circuit diagram, this is my armature current IA, this is my load current IL. So both are same, isn't it? Both are IA is equal to IL. So the power delivered to the load can be given by V into IA or V into IL. The power developed in armature is given by EG into IA. So this is, pardon me, this is not EB, this is EG. So EG into IA. And as I already mentioned, IA armature current is equal to load current IL. And if I apply KVL to this loop, assuming here this is the positive and this is negative, I'll get this equation: EG is equal to V plus IARA plus 2 into brush drop. So this is the expression for generated EMF in case of separately excited DC generator. Coming to self-excited DC generator, so it can be defined as a DC generator whose field winding is excited by the current supplied by generator itself. So here you can observe very carefully that the field coils can either be connected in series to armature, or they are connected in parallel, or partly they are connected in series and parallel. So depending upon the connection of armature coil as well as armature and field coils, they are further classified into three categories: series wound generator, shunt wound generator, compound wound generator. If the field coils are connected in series with armature, it is called series generator. If the field coils are connected in parallel with armature, they are called shunt wound generator. If the field coils are partly connected in series and partly connected in parallel with armature, they are classified as compound wound generator. So first we'll see series generator. Yeah, this is EG, mind you. Okay. Uh, so as you can see here, this is IL, which is load current, ISC, series field current, armature current, IA. So the first series generator. So I told you in here the field coils are connected in series with the armature winding. That is why the name series generator. So the series field will carry the armature current, and the series field winding will consist of very few turns of thick wire of larger cross section area. Okay, so the resistance will be of very less value, less than 1 ohm. Okay, so because the armature current is very of high value, so its resistance will be very less. So power delivered to the load will be V into IA, okay, or VA into IL, or V into ISC. Since all the three currents are in series, you can see all three currents are in series, isn't it? So all three are same in this configuration. Series generator, IL is equal to IA is equal to ISC. So that is why power delivered can be either written as V into IL, or V into ISC, or V into IA. Power delivered or developed in the armature, PG is equal to, so here also it is not EG, it is EG. Okay, so EG into IA. And if I, so that this already I have told you, IA is equal to IL is equal to ISC. So if I apply KVL equation here, I'll get the expression for generated EMF to be V plus IARA plus ISC plus 2 into brush drop. Next, coming to shunt generator, this is the circuit configuration of shunt generator. Here this is also EG. So here the field winding is connected in parallel with the armature, that is why it is called shunt generator. So here the entire terminal voltage is applied. Here very small current ISH is flowing through the field winding. It has many turns. The resistance is also very high. So ISH, shunt field current, is given, can be given by V by RSH. Power delivered to the load is V into IL. Mind you, here the current flowing through the load is only IL, so that is why I can only write V into IL. Power developed in armature is EG into IA, and if I apply KVL in this loop, I'll get the expression for generated EMF to be EG is equal to V plus IARA plus 2 into brush drop. And at this junction, if I apply KCL, entering current is IA, leaving currents are ISH and IL. Okay, so according to KCL, my IA will be IA will be equal to load current IL plus shunt field current ISH. Coming to compound generator, so here the field current is partly connected in series and partly connected in parallel. So depending upon the connection of shunt and series field winding, they are further classified as long shunt and short shunt compound generator. This is the circuit configuration of long shunt compound generator. So ISH will be V by RSH. IA is equal to ISC. You can see from the circuit configuration, IA is equal to ISC. Power delivered to the load, so the current flowing through load is only IL, so therefore power delivered to the load is V into IL. Power developed in, this is EG, power developed in armature will be EG into IA. Again, if I apply KVL to this part of the circuit, that will give me the expression for EG to be V plus IARA plus ISC plus 2 into brush drop. If I apply KVL at this node, I'm sorry, if I apply KCL at that node, entering current is IA or ISC, leaving currents are ISH and IL. So IA will be equal to IL plus ISH, or I can also write ISC is equal to IL plus ISH. Coming to short shunt, you can observe the, so if I make you observe the main difference between long shunt and short shunt, you can see in long shunt the shunt field winding is parallel to both series field winding as well as armature. But coming to short shunt, you can see the shunt field winding is parallel only to the armature. That is the main difference between long shunt compound and short shunt compound. So here also the generated EMF is CEG. If I try to write the equations depending upon the circuit diagram, so my ISH shunt field current will be V plus ISC RC divided by RSH. So previously it was V by RSH because you can see that the voltage across the shunt field winding was terminal voltage, isn't it? In case of long shunt, since these are parallel, this is parallel, this branch is parallel, in parallel the voltage is same, so the terminal voltage V will appear across the shunt field winding in case of long shunt compound. But in this case you can see the voltage across shunt field winding is not V, but it is V plus the drop across the series field winding. Okay, so that is why I have written ISH as V plus ISC RSC divided by RSH. The load current, if I is IL, is same as series field current IL. From the circuit diagram you can analyze that. Power delivered to the load is V into IL, or I can also write V into ISC since both are same. Power developed in armature is EG into IA. So again, if I apply KVL, that will give me the expression for EG to be V plus IARA plus ISC RSC plus 2 into brush drop, and upon applying KCL at that node, my armature current IA is equal to IL plus ISH. As I told you in the classification, that compound is further classified into cumulative and differential. The main difference between cumulative and differential is, in cumulative compound both the fluxes, that is flux produced by series field winding as well as shunt field winding, will assist each other or aid each other, whereas in case of differential compound, the flux produced by series field winding as well as the shunt field winding both will oppose each other. So that is the main difference between cumulative compound and differential compound. So this concludes my today's lecture on the types of DC generator, that is different configurations, as correspondingly we also discussed the governing equations. So until we meet with some other topic in the next lecture, take care, goodbye, thank you.